This social robot watches another robot which acts as a teacher. Once it can model the teacher, it can try and figure out how could I do this action better than the way that the teacher is doing it. But what happens when you have 3 robots or 3 people all learning from one another or working together, collaborating to try and achieve something? And then you get into what's known as the study of social networks.
There is a transition, I think, in the social sciences where you move away from just having ideas, abstract ideas about how society should function, how an economic system should function. We can go and look. Now we can go and look. We just did not have that data before.
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.
Hi, I'm Amy Seidel, and welcome to Emerging Science. This week, we're taking a look at the intersection of technology and social science. With the continued advancement of technology and digital communication, we find 2 intriguing developments. Obviously, advances in the internet and information technology are changing the way we communicate, gather information, and function as a society. Perhaps not as obvious, but just as thought-provoking, is the application of developmental psychology toward the advancement of artificial intelligence. Josh Bongard at the University of Vermont is collaborating with child psychologists to teach robots how to learn.
Like many young boys and girls, I was interested in robots and saw them in stories and in movies. I didn't understand why they weren't in the real world. Where were all of these robots that you saw in the movies? And I guess that question never really left me. There are applications for robots. So first of all, we have industrial robots. So most factories in North America and most factories around the world, if you go into one of those factories, there's more robots than there are people. So we know how to build robots that do the same thing over and over again. But the moment you move outside of a factory to the out of doors or into our homes, nothing is ever the same twice. Well, there is a very successful robotics company in Boston, iRobot, and they've developed the Roomba, which is a robotic vacuum cleaner. So the floor of your home is relatively simple. The robot simply needs to move around and vacuum the floor. When its bin is full, it knows how to go and empty the bin. It knows how to find a wall socket to recharge itself. So we're moving in that direction. But again, the floor of somebody's home is a relatively simple environment.
Since the advent of computer-automated manufacturing, our society has been influenced by robotics in the workplace. As Josh describes, it's very common to see robots performing repetitive tasks in controlled environments. But why don't we see them more often integrated into our modern society?
There are 2 main issues, I think, about why we don't have robots in our homes or working with us out of doors. The first one is a hardware challenge, has to do with batteries. It's one of the challenges we're facing with hybrid cars. We can't power our robots without a cable to an electrical socket for a long period of time. The other challenge is intellectual, which is that we don't really understand what we mean by intelligence. How is it that we accomplish tasks in the real world? So one application that I'm interested in is construction. For example, if the robot is programmed to move a pile of bricks from point A to point B, there might be people near the pile of bricks, so it needs to be very careful. The pile of bricks is never going to be exactly the same from one construction site to another, so how does it know how to deal with bricks of different size? What happens if it starts raining? What happens if the site where it needs to move the bricks is on the other side of a road? It needs to know something about cars and safety and so forth. It sounds relatively simple, but you could see how machines like that would start to work alongside humans and allow us to build things on a larger scale, to build them more cheaply, and so forth. So that's my personal goal. A lot of the insight that we gain into intelligence comes from insects. Biologists are beginning to know a lot about insects and how they see their world and how they react to it. So insects are quite sophisticated machines, if you like. but a lot of their hardware is relatively simple. So a lot of insects have relatively few neurons and synapses, and they are able to do a lot with that simple machinery. So can we take insights from insects and build that into our robots so that they do simple things like insects, for example, moving towards a light source, moving away from a light source, finding an object of interest, picking it up and moving it somewhere else. Once we master those skills, then we can start to look at more sophisticated organisms, like mammals, for example, and say, what is it that's different between mammalian intelligence and insect intelligence? The robot that I'm going to show you now in the lab is a social robot. This is somewhat different from some of the examples I've given already. Primarily what we're trying to do is study what we call intelligent robots or adaptive robots. So what we'd like to do is eventually create robots where we tell them what to do, but they figure out on their own how to do it. One of the ways that we do that as humans when we're young is to learn from another, to learn from a teacher. So developmental psychology is about how do children learn, how do they transition from infants into functioning adults. And one of the things that we all go through at a very young age is that very quickly we learn how to imitate. But at a certain point we go beyond imitation and we go on to inferring intent. So if I observe a teacher trying to perform an action, for example separating a pen, but they're not holding the pen in the right way, the student can infer that the teacher is failing at the task, and when you give that pen to the student will, rather than imitate the teacher, will grab the pen in a different way, separate the cap from the pen, and give it back to the teacher. So one of the projects in my lab has to do with this robot that you see here. This is an experiment that's partly finished. Eventually we will have two of these robots facing one another. One of the robots will be the teacher and the other robot will be the student, and the student will learn from the teacher.
That's fascinating. Can you show us how it works?
Sure. So as you can see, this is our robot here, and this work is in progress. So eventually what we'll have are two of these robots facing one another. We'll have the student robot and the teacher robot. But for the moment, the single robot is going to serve as both the teacher and the student. And what we're going to do is, first of all, the teacher is going to demonstrate a particular action. So if you assume now that this is the teacher and there's a second learner robot that's watching our teacher here, our teacher is performing now a very simple action, which as you see is just to lift this object. And so now that the learner has seen the teacher do that, the learner will discover what the game is, which in this case is a game of lifting objects. So the learner has already picked up on something from this social interaction. And now our teacher is going to perform exactly the same action, but as you can see, it's now going to try and lift a very different object.
So this time the teacher fails.
Unfortunately, this time the teacher fails, and the student sees this, realizes that the teacher is limited in some regard. The teacher always performs the same action, so the learner knows that the game here is to try and lift objects. So in this third phase now, if you can see on this back computer here, the learner is now thinking. It's doing what we call mental rehearsal. It knows that the game is to try and lift objects, and it now needs to discover a new way of moving beyond the way in which the teacher moved, and it's trying to discover a particular way of moving that will allow it to successfully pick up this new object.
They're using a different technique.
Absolutely, and it's quite a simple change, but basically our learner has now learned that before it lifts the object, it needs to close its hand, which the teacher never did. So the student here has discovered something beyond what the teacher knows. And although the actions themselves are simple, what's powerful here is that the learner has demonstrated that it can improve beyond the teacher, and that is a real hallmark of social intelligence, to build on this interaction between learner and teacher and eventually go beyond what the teacher is capable of.
Josh, you're a computer scientist with a background in mechanical engineering and mathematics, and yet your experiments seem to be probing into some philosophical realms, like what is human intelligence? How do you confront that philosophically as well as from a more natural science perspective?
That's right. So for us, obviously, we're very firmly entrenched in mechanical engineering and computer science, but it does start to suggest to neurophysiologists, psychologists, and even to some degree philosophers, what does this say about the human condition? Do we actually perform mental simulation like our robots are? And does it say something about the nature of self-awareness? This robot has an understanding of itself and mentally rehearses what would happen if I did this. What would happen if you have 3 robots or 3 people or dozens or hundreds? How would they self-organize? How would they learn from one another to achieve a complex task that's beyond any one robot or beyond any one person? And then you get into what's known as the study of social networks. How do people influence one another? How do people learn from one another? And by building robots that learn from one another, that's one approach to investigating social networks.
Certainly, Josh and his colleagues are taking technology and robotics far beyond the reaches of traditional computer science and mathematics, to human development, social science, and even to philosophy. Next, we turn to how the social sciences are affected by technological advancement, from understanding behavior patterns of individuals, groups, and to entire societies.
If you understand how individuals behave, that's great. You also then need to understand how they're going to behave in a group. I think that, the internet is our playground for developing these experiments where we understand how individuals behave and then how their behavior changes as a result of interaction with other people. Some of the things that we've looked at in particular are blogs. So here are people keeping an online diary of what they're thinking about as they go through the day, at a vast scale around the world at any given time, and it's all available for us to download.
And some of our work in particular then is looking at emotions, how emotions spread, the contagion of emotion, if you like.
We've started to collaborate with Jonathan Harris and Sepp Kamvar, these creators of a website called wefeelfine.org.
We've been harvesting data from. They, of course, in turn have been harvesting data from blogs. Any sentence that starts with I feel or I am feeling, they pull that off a blog, and then you have a timestamp. And in some cases you have the age of the blogger and where they live.
Over the last 3 or 4 years, they've gathered over 10 million human feelings that have been posted on the internet by 2 million individuals. So what we've done is taken their data, all those sentences that express human feelings, and we've tried to assign some mathematical score to the emotion being expressed. So the way we do that is we take a psychology study that was done at the University of Florida where students, intro psych students, were asked to rate on a scale of 1 to 9 how happy they feel when they read particular words. So the word triumphant, for example, was deemed to be a very positive word, one that made people feel good. So every time we see one of those words in one of these blog sentences over the last few years, we assign a particular, that score, the average score that the psych students had for that word, we assign that to that sentence. And in that way, we're able to kind of quantify the emotion being expressed.
This is really getting at a fundamental problem for measuring how well society is doing. But how do you measure that?